Thank you, Sarah, for the introduction. Today I'm going to talk about the use of a temporal planner in combination with an external solver in order to model and solve problems involving electricity network. This research is part of a bigger project called the Autonomic Power System, and the aim of this project is to look at the future energy scenario that we expect in 2050. During this period of time, we expect changes both from the generation side and the consumer side. And this implies an increase of the complexity of the network. In the future, then, we want to rely on a centralized approach. Instead, we decompose the network into different zones of control. So in this talk, I'm first of all introduce a power system, what is a power system. Then I'll explain a PDDL model that can be used to model this kind of problem. I'll then talk about the external solver that we use in combination with the planner, and finally I'll give you some evaluation. So an external power system can be defined as a critical infrastructure aimed to deliver electrical energy to final users. So we can identify different phases. We have the generation part, in which we convert different forms of energy into electrical energy. The electrical energy flow is brought to an higher voltage, so it can be efficiently transmitted through the transmission network through wide areas. Then the electrical energy is brought to a lower level, and it flows into the distribution network, so it can reach the final consumers. In this slide is the power system as it is now. In the future, we expect changes from the generation side, so we will have renewable resources connected directly to the distribution network, and also different type of consumers. If we look more formally on how we can represent a transmission or distribution network, we can say that we have the generators that produce active and reactive power. We have also transformers that regulate the voltage flowing through the electrical network. We have bus bars. Bus bars are basically strips of electrical conductor that connect to different parts of the network. We have lines that are the means in which the electrical energy flows, and finally we have loads that consume the active and reactive power. The problem that we have with power system is that we don't have large storage devices. So this means that we need to satisfy the demand at every time instant. In the meanwhile, we want also to maintain some constraint on the network. For example, we want the voltage to lie within a given bound, or we have a threshold on the power flowing to lines. And what makes this an interesting problem is also the presence of temporal constraints. So the problem that we are trying to solve is a different problem from the PSR domain that was proposed a few years ago, in which they were looking at the connectivity of the network. In order to model this problem, we need a set of applicable action. For example, we can increase or decrease the power generated. We can step up or step down the tap of transformers. The tap are piece of transformer, and regulating the level of this tap is possible to set different output voltage of the current. We can shed loads, and we can turn on or off switches, and so on. In this model, the numeric constraints that we have on the network can be modeled as overall conditions of actions. As I said before, we need to maintain the balancement of the network for a given period of time, in which the load behavior varies. So this can be modeled in PDDL with numeric time initial fluence. So for example, we can say that at time 0, the load 1 consumes 7.44 unit of power, while at time 1, the consume is increased of a given quantity, and so on until we describe a period of time, in this case 1 day. This is an example of PDDL action. The problem that we have with this kind of domain is how we can describe the variation of some quantities. For example, in this action, we want to step up a tap of a transformer. And if we do that, we change the voltage level at the busbar of the network. And the problem that we have is that this quantity are related to each other with the power flow equations. The power flow equations are a set of nonlinear equations, and this means that basically the effect is not linear. Moreover, we have the changing a tap of a transformer of the network change all the busbars, all the voltage of all the busbars of the network. And this is like the ramification problem that we have in NERI. And of course, the change is different from busbar to busbar. So the approach that we use is to recognize that there are two different levels of effects. We have the direct effect and the indirect effect. In our example, the direct effect is the change of the tap level of the transformer. And this implies a change in the voltage of the busbar. There are other domains that present this kind of structure. For example, in the maze ball domain, we have a table, and on top of this table, we have a ball. Inclining the angle of this table, the ball changes position. So we can say that the change in the angle of the table is a direct effect, and the change in the position of the ball is a indirect effect. One thing that we have to consider is, of course, the link between the direct and the indirect effect. For example, in the PSR domain, this link was made by Axiom, and in a hypothetical domain in which we have a DC circuit, we can use an extension of the Axiom that handles numeric variation. In the maze ball domain, because the interaction between the dependency between the angle of the table and the position of the ball wasn't trivial, the approach used in the paper was to precompile a lookup table with all the possible values that we have. In our case, this approach is not feasible because changing, for example, a tap of a transformer change all the voltage of the network, and vice versa, the voltage of the network is determined by all the transformers. So the size of a lookup table will increase exponentially. What we use instead is an external solver. So we have a planner when we have a numeric state. We can divide the variables in this numeric state in three categories. We can say that we have these special variables that are the numeric variables that describe indirect effects. The dependent variables are the numeric variable that describe direct effects, and we have also a third category that has a direct effect, but this influence any of the social variable. So when a planner evaluates a state, it calls an external solver and it passes the dependent variable. The external solver with an optional input that does not depend on the state calculates the special variable that are used in the planner. In our specific implementation, we use as a planner POPF because it's the only temporal planner capable of dealing with numeric time initial fluence. And for the external solver, in the first outset of our implementation, we use IPSA, the power engineer software, specialized in the power flow equation solution. But due to the expensiveness of the call of this external solver, we decide to implement a module that solves the power flow equation with Newton-Raphson method. So when the planner passes to the external solver, for example, the power consumed by the loads that are stated with time initial fluence, and for example, the other parameters, for example, the power generated that can be set and can be chosen with actions. The external solver calculates, for example, the power flow into the lines, the voltage that then are used during the evaluation of the state. For the heuristic, we use an approximation of these power flow equations. So, for example, we can say that if we step up the tap of a transformer, we increase the voltage of a busbar. But because we have numeric time initial fluence, we need to be more specific during the heuristic evaluation. So for example, if we don't, if we take the heuristic evaluation as it is in POPF, that in POPF is performed with a temporal relaxed planning graph, the effect of the time initial fluence with respect to the open actions is ignored. So in our relaxed plan graph, basically we don't have any action. Instead, we need to call the external solver to calculate the exact value that this time initial fluence causes. And if we discover that we violate one of the constraints that we have, for example, in this case we violate the voltage constraint, we add to the relaxed plan graph an action that restores this value. Okay, so in order to evaluate our implementation, we perform two different experiments. The first is to verify the scalability in terms of sites of the network, and the second is to verify the scalability in terms of number of possible choices that we have. For the first experiment, we use this network. We have a slack generator for which we have a limit on the power that it can produce. We have bus bars. And we have this constraint on the voltage. We have a threshold on the power flow into the line. The load is assumed to be predictable and known in advance, so it can be modeled with time initial fluence. We have a generator for which we can increase or decrease power, and we can also shed a load, but still maintaining a minimum power to be satisfied. So for this experiment, we use different load profiles taken from the UK historical data, and we use a network with an increasing number of bus bars. So in this slide, I show you on the left plot the number of states evaluated as function of the number of bus bars for the different load profile that we have considered. So we can see that increasing the number of bus bar, the planner on average evaluated the same number of states. what changes is the execution time over the number of states evaluated. And this quantity gives us an indication on the time spent to evaluate a single state. Right. So we can see that increasing when we have a network with more bus bars, we have an increase of time spent to evaluate every state. And this is because basically the external solver needs more time to compute the solution of the powerful equations. For the second experiment, we use this 33 kV overall network, for which we have 61 bus bars, 64 lines, and different loads. The problem with this network is that for some load configuration, we have a problem with the voltage on some bus bar. So we need to turn up or turn down the tap of some transformers. Again, we use different load profile, and we use network with an increasing number of transformers. So we start from 3 until 24. And these are the results. Again, on the left plot, we have the number of states evaluated as a function of the number of transformers. And you can see that when the planner finds a solution, for example, with 3 transformers, also adding other transformers, so basically adding more choices that the planner can choose, it still can find a solution with the same number of states evaluated. And again, what changes is the execution time over the number of states evaluated, because again we have that an increase of the complexity of the network brings us an increase of time spent to evaluate a single state. So, concluding, in this talk we have presented the challenges that modeling an electricity network presents. This is because we have nonlinear effects, and we have actions that has an effect on all the elements of the network. In order to overcome this problem, we use a coupling of an external solver to a planner, and we need also to refine the heuristic evaluation in order to improve the performances. For the future, we want to improve further the heuristic evaluation, and we want to also consider model cost of the action, that in this case is the actual market cost of producing power. Another important field that we want to consider in the future is are the uncertainties that we can have when we consider stochastic generators. Thank you.